it is Mrs. Kreider, and I am going to show you all about special right triangles today. There are two special right triangles. One is called a 45-45-90 and the other is called a 30-60-90. They're called that because those are the measures of the three angles. Of course, one is 90 because they are special right triangles after all. And what we're going to do is I am going to show you a pattern of behavior that happens with these two kinds of triangles that helps us to find side lengths without doing any math. That means no Pythagorean theorem and it means no trigonometry. So that sounds appealing to you? Go ahead and keep watching and let's see why we can do that. First, let's start with a simple example of a right triangle with a 45-degree angle and another 45-degree angle. Okay, making that isosceles, and of course that's why the legs are congruent, but we want to find what the hypotenuse is. So I'm going to do the Pythagorean theorem. Now the Pythagorean theorem, and I'll write it up top, a squared plus b squared, that's the two legs, equals c squared, which is always the hypotenuse, which is across from the right angle. I'm not going to rewrite this every time, so I'll keep this up here so that it's fresh for your mind. And let's just go ahead and substitute the numbers. 1 squared plus 1 squared equals c squared. Okay, 1 squared. What is squaring? That means you're multiplying by itself. 1 times 1 is 1, plus another 1 equals c squared. Now, we have c squared, but we always need to simplify to the actual variable. We want to know what c is. So in order to undo a square, we need to take the square root. That is the inverse operation for squaring. So I am going to simplify over here to a 2, and I'm going to then take the square root of both sides of this equation. So this radical and this square will cancel each other out, and I get c equals the square root of 2. Might be easier to remember if you think the square root and the square cancel. So c equals the square root of 2. So far, I have nothing special to look at. And you might be saying, oh, Miss Kreider, but I want to use decimals because they're easier. Okay, but you'll miss the pattern completely if you work in decimals for this. So we are going to go ahead and continue with another example, and I'm going to keep working with that square root symbol because that's how we're going to spot our pattern. So let's go back and we're going to do the same thing. We're going to identify c by using the Pythagorean theorem with our two legs. Again, these are congruent because they are isosceles. And this is going to be 2 squared plus 2 squared equals c squared. 2 times 2, which is 2 squared, that's 4, plus another 4 equals c squared. 4 plus 4 is 8. And again, we need to take the square root of both sides, and the square root and the square will cancel, so we get c equals the square root of 8. Okay, so far I'm not seeing anything special because the square root of 8 and the square root of 2 do not look like they make a pattern. However, the square root of 8 can be simplified because it has a square root, or I'm sorry, it has a perfect square as one of its factors. So let's look at the factors of 8. And I do them in pairs to make this an easier process. 1 times 8, well, that's not going to work because that doesn't simplify it any further. 2 times 4, and hey, that one actually looks kind of special because 4 is a perfect square number. So I'm going to rewrite this as 4 times 2, and that does not look much like a 4. 4 times 2 equals c. So the square root of 4 times 2 equals c. I'm going to reach down here and extend my page a little bit so that we can keep seeing what we're working on. And I'm going to bring down these calculations so that they are lower and I have room. Now I can finish up. So I'm going to rewrite this as the square root of 4 times the square root of 2 equals c. I can do that because I'm multiplying these two factors. If this was 4 plus 2, I would not be able to write the square root of 4 plus the square root of 2. It's a rule that works, it's a property that works for multiplication and division inside a radical. So now that I've rewritten it like this, I can say, oh, well, 4 is a perfect square. So the square root of that perfect square is going to be 2. 2 times the square root of 2 equals c, and I'm going to go ahead and write that at the top. 2 times the square root of 2. Okay, so far I'm starting to think I might have a pattern going because I have this square root of 2 here, and I have another square root of 2 here. So I'm thinking if I have a third example, I might just get a square root in the hypotenuse. And if I look at the number in front of the square root, what do you think? Do you think it could be 3 times the square root of 2? That's what I think. Let's try it. 3 squared plus 3 squared equals c squared. 3 squared is 9. That's 3 times 3 plus another equals c squared. 18 then equals c squared. And since I already know I need 2 to be a factor, I'm going to see what does 18 split up into where 2 is a factor. 9, you say? You are correct. I'm going to write this as 9 times 2. Oops, I forgot to take the square root first. Boop, boop. Now I can say c equals the square root of 9 times 2. And I can rewrite that as the square root of 3. Why do I keep doing that? I'm going to rewrite that as the square root of 9. I'm trying to jump the gun. Square root of 9 times the square root of 2 equals c. And since 9 is a perfect square, the square root of that square is going to be 3. 3 times the square root of 2 equals c, and I get 3 times the square root of 2. And bazinga, the pattern I suspected has actually held up. The leg was 3, and the hypotenuse was that same leg amount times the square root of 2. The leg was 2, and the hypotenuse was 2 square root of 2. The leg was 1, and could I argue that this is 1 times the square root of 2? I think so. So how does this help us? Well, let's go to a different example where their numbers are bigger. If I start squaring these with Pythagorean theorem, it's going to be 128 by the time I'm at this step. And the numbers are getting hairy. What if this was 16? What if it was 20? Well, we can skip all that by saying, hey, the leg is 8. If the leg is 8, then I know, I know since this is a 45, 45, 90 triangle, that this is going to be 8 times the square root of 2. And I'm done. Perfect. So let's take a look then at the rule. This is what you'll see on your end of course reference sheet. And of course, this simply means that if x is the leg, then x times the square root of 2 is going to be the hypotenuse. And sometimes you'll see that this might be listed in a problem with a different variable, and I'm going to show you that in a second. But just know if you see 45 and 45, this is isosceles, and these two have to be congruent. Okay, I'm also going to show it to you in words. The hypotenuse equals the leg times the square root of 2. So if you can just remember that relationship or know how to interpret that on your end of course reference sheet, then you are going to have an easy peasy way to solve these kinds of triangles without doing any heavy lifting. Let's take a look at an example which this might pop up where you have the hypotenuse given. Well, hey, wait a minute, that's not fair. You didn't give us the hypotenuse before. That's okay. The hypotenuse is the leg times the square root of 2. So the leg must be 4. So I'm going to go ahead and put 4 equals x. And again, since this is an isosceles triangle with congruent base angles, I know that x and y need to be equal to each other. That's that tricky thing I was talking about. And this may pop up for you. So just don't let the x and the y trick you that they're different letters. This also equals 4. So your legs are 4 and your hypotenuse is 4 root 2. Okay, let's go ahead and move on to the 30, 60, 90 triangle. This might be my favorite one. This is a 30, 60, 90 triangle, and I'm going to start with an equilateral triangle. Why on earth, Miss Kreider, are you starting with an equilateral triangle? Well, it's because if I were to draw in, and I'm just going to kind of sketch it in, if I were to draw in the altitude here, it makes a right angle because the altitude of a triangle is always perpendicular to the base. But a special property of an equilateral triangle is that the altitude also cuts our opposite side, our base, into two congruent pieces. Okay, and it cuts this into two 30-degree angles. You see where I'm headed with this? 30, 60, 90. And let's go ahead and reveal the separate drawing that I have for you. 30, 60, and 90. Oops, I forgot to show you my 2's. I have these marked with leg lengths of, or side lengths of 2, 2, and 2. And the reason for that is because if all three of these sides are congruent, but I know that this altitude splits this into two pieces that are the same length, then I can take that 2 and divide it up into lengths of 1 and 1. Then when I cut over here and look at my other triangle, I say, oh, hey, the short leg, the one that's across from that smaller angle, is always going to be half of the hypotenuse because it's half of an equilateral triangle. So if you can remember that little visual trick, you will always be able to remember these two pieces and how they relate to one another. It's this one that we're going to pay a little more attention to, this long leg that we call it. Short leg, long leg. Long leg is across from the bigger of those two angles. And we're going to do a little bit of work to see if we can define or see if we can pick out another pattern. I'm going to extend my page so I have a little more room to work. And we're going to go ahead and jump right into, hey, this is a 30, 60, 90. The side length is 2. And since that is the hypotenuse, I know that the short leg, which is across from the 30-degree angle, is half of that. So it's going to be 1. Same exact example we're using here. And if you struggle with this, you can always just kind of draw in the equilateral triangle and then go, oh, okay, this would have been 2, so that's 1. That may help you to keep straight which one is which for the two sides. But let's go ahead and call this C for our hypotenuse, and we're going to call this one A, and we need to solve for B. I'm keeping this B on purpose because I like the way it works in the Pythagorean theorem. And again, I'll write at the top, A squared plus B squared equals C squared. That's our friendly Pythagorean theorem that we're going to use to see if we can identify yet another pattern. So let's go with 1 squared plus B squared equals 2 squared. 1 squared is 1 times 1, that's 1, plus B squared equals 2 times 2, which is 4. I need B by itself, so I need to first undo what's being done to it. 1 is being added, so I need to subtract 1. B squared now equals 3. So to get the B by itself, I have to take the square root of both sides, and remember the square root and the square cancel each other out. So I get B equals the square root of 3. Okay, once again, I don't see anything special yet, but I will, I promise. Why do I keep hitting that button? Okay, so let's go ahead and reveal another one. Now, the hypotenuse is 4, which means the short side is going to be half of that, which is going to be 2. And then we'll call this B, and this C, and this A. And then let's do the Pythagorean theorem again. So we've got 2 squared equals, 2 squared plus B squared equals 4 squared. 2 times 2 is 4, plus B squared equals 16. Remember, 4 squared is 4 times 4. It is not 4 times 2. So we're going to subtract 4 from both sides to undo what's being done to the B. We need to get it alone. B squared equals 16 minus 4 is 12. I'm going to need to extend my page again. And now I have B squared equals 12. When I take the square root of both sides and I cancel out my radical, I get B equals the square root of 12. Well, just in keeping with the pattern that we found in the 45, 45, 90s, I'm going to jump to this idea that I bet you we're going to end up with a square root of 3 here, which means I bet you I can split this into something times 3. What times 3 equals 12? 4, you say? You would be correct. 4 times 3 equals 12. We can rewrite that as the square root of 4 times the square root of 3. The square root of 4 is 2, so we get 2 times the square root of 3. So our B, our long leg, is 2 times the square root of 3. Let's do it again. One more. Let's see if we can really lock in this pattern. Now we have 6. Again, short side is half the hypotenuse, so the short side is 3. We'll call this B. 3 squared plus B squared equals 6 squared. 9 plus B squared equals 36. 3 times 3 is 9. 6 times 6 is 36. We need to undo what's being done to B, so we will subtract 9 from both sides and leave B squared equals 27. We're going to take the square root of both sides, and we're going to cancel our square root and our square to get B equals the square root of 27. And I'm going to rewrite that as, you got it, 9 times 3. Because I know I want a 3, so I just do what times 3 equals 27? 9. Rewrite as the square root of 3, square root of 9, I think I've done that 4 times now, times the square root of 3, b equals 3 times the square root of 3. Okay, now if this is 3 times the square root of 3, I think I'm starting to see something that's pretty interesting here. If I know the hypotenuse, I know that half of that is the short leg, and then the short leg times the square root of 3 is the long leg. I can do that here too. I know the hypotenuse, cut it in half to find the short leg, multiply that times the square root of 3. Okay, I might also be given the short leg. If I'm given the short leg, I can double it to get the hypotenuse, and I can multiply it by the square root of 3 to get the long leg. So there's a deep connection going on here between these two different sides when all we needed was one side and to know that it was a 30, 60, 90. Why is this special? Okay, what happens if we have a big nasty hypotenuse like 30? Well, again, I'm going to exclaim to you that I don't need to do any math. I can simply recognize, hey, this is a 30, 60, 90. This is the hypotenuse. Okay, 30 is the hypotenuse. The short leg is half the hypotenuse, so that's going to be 15. And the long leg is going to be 15 times the square root of 3, because that's the pattern we developed. So the rule for 30, 60, 90 looks like this, and this is exactly what it looks like on your end of course reference sheet, and I'm also going to give it to you in words. The hypotenuse equals 2 times the short leg. The long leg equals the short leg times the square root of 3. So whatever you're given, you can write the other one, or you can figure out what the other one is valued at. And let's do one final example. This is something you might see on an end of course exam. This is exactly the kind of problem they like to give. So in this case, I'm given a triangle with one of these angles marked, and I know this is a 90-degree angle, and I know these two have to add up to 90. So that means this is going to be 90 minus 60, which is 30. So now I know I'm looking at a 30, 60, 90 triangle, and I am being given the short leg, the x. So the hypotenuse is going to be equal to 2 times the short leg. So the hypotenuse is going to be equal to 16 in this picture. The hypotenuse is across from the 90-degree angle, so that is going to be 16. The long leg is equal to the short leg, which is 8, times the square root of 3. So I can simply write 8 times the square root of 3. It wouldn't have mattered if I had been given the 16. I would have just cut that in half to make the 8 and then multiplied times the square root of 3 to get the long leg. As long as you're given one of these two, you are in good shape. If you are given the long leg, if it has a square root of 3, you can just use the number in front. If it doesn't, then you have to divide by the square root of 3, which involves rationalization. And again, that's another lesson. For now, we're done, and I just wanted to give you that overview so that you have a little bit more depth to your understanding of special right triangles and why they're important. Okay, thanks and have a wonderful day.